So, hi everyone. So this is a nice little cloud talk, I think. For those who don't know me, which is probably all of you, I'm kind of a software engineer slash architect slash engineer. So it really depends on what time of the day it is, what kind of I'm doing currently. My main responsibility is basically building a platform as a service in the cloud. Platform as a service is basically some databases, maybe some observability service, maybe DNS, all these kinds of things. So my free time I like to dig deeper into other topics like databases. I'm also giving some cool lecture about it at the DHBW. And I'm writing blog posts on Medium. Here you can find my socials if you want to connect with me. Feel free to send a request on LinkedIn. So what does the talk is about and what leads to the talk? So we see many new cloud providers building some kind of cloud service, right? So here on the very right, we see Ivan, the nice little crab. It's not a Rust crab Ferris, it's their own crab. They are providing data services on multiple clouds, on multiple public clouds like GCP, AWS, Azure, and I think now even some smaller thing, DigitalOcean it was. Then we have software vendors like Confluent and Grafana. They are building open source software and now are on the challenge, how can I make money with it? The obvious thing is build enterprise features, but the other thing is build a cloud solution. That means taking care about the operation part. And this is what these guys are basically doing. And then we have real cloud providers which has their own data centers, their own services on top of it, maybe even SaaS solutions like AWS and STACKIT. It's a small German cloud provider where I'm working in. That's why I have some nice little shirt from them. What is a managed service? And why should you even use it? Because nowadays I heard a developer saying, okay, I really need a managed service, otherwise I can't really work, because nobody wants to take care about operations, for example. We have operational knowledge. Like, have you ever operated some PostgreSQL? Have you done some backups of it? Have you done a replication? Raise your hand. Wow, that's many. So you may know that's quite a pain to handle, because it's not about only setting it up once, but then you have to maintain it. The first thing is you have to do updates and upgrades. Maybe you go from Postgres 13 to 14 at some point, then to 15, and then you know, okay, I need to get some logical backup, upgrade it, and replay the logical backup, something like that. Then you need to take care about scaling up and down. Maybe you have some more data at some point, and you need to resize the disk. Maybe you're running out of RAM. So all these pain points are handled by a managed service for you. You only get the interface. Here's the order button. Feel free to go, and we will handle everything in the background. Here are some examples of common managed services. There is Kafka. This is really a pain in the ass to operate, but really nice to use, actually. Then we have Postgres, some other databases like MongoDB, Influx, or message queues like RabbitMQ. So let's dive deeper into what I want to talk about. I don't want to talk about really about operating the services, but rather building a management lane, so really building this cloud product. And what we have to provide as a provider is some kind of functionality to provision, update, and deprovision this instance. An instance could be a Postgres, an Influx, a Grafana. Then we have to provide some functionality for backups, obviously. So a customer needs to create backups, he needs to list all his backups, he needs to get a state of the backup, and finally also restore some backups. Then what's really common in our case is ACLs, because I believe we don't really have some virtual private network. That's why we are restricting the network with ACLs. It's some IP range restriction. And then, of course, config management. So the challenge is actually quite easy on the first side. We have on the left here a client. It could be Terraform. It could be some UI where you interact with the service. You want to list all your service instances, see what I have, then get more information about all the other configs like backups, ACLs, and so on. And what we usually do is sending an HTTP call in the REST philosophy, because Terraform is built on it. Some web UI is built on it. I believe we don't use other protocols like gRPC, which would be cool, but we don't. And this REST API then in the background needs to deploy the instance on some compute. And back in the days when we started with STACKIT, and I started with the awesome observability service, which consisted of Grafana, Prometheus, Thanos, an alert manager, and later on Loki and Tempo. So a similar offering to, I think it was Logs.io, where they built also this observability platform. We evaluated, okay, where can we host the components for the customer? And we basically had two options. One was virtual machines and one was Kubernetes. And there were different criteria which we evaluated, like how we can scale the instances for customers, how easy it is to maintain, what is the environment, how I can do updates and upgrades. Can I do zero downtime deployments easily? And so at the end of the day, we decided to go with Kubernetes because it was the low-hanging fruit. It was really great to set up. We could just run helm install, get an operator, then apply some operator CRD, and it did all the magic in the background. For example, for Prometheus, there's a Prometheus operator. Then for Grafana, there was no operator at all, but it doesn't matter because it was a simple deployment. For Postgres, there's a Postgres operator from Zalando, if you might know that, and this is really simplifying things of hosting. So that means we can revise the challenge a little bit. We have now a REST API and multiple Kubernetes clusters where we can deploy our instances to. Because at some point, the Kubernetes clusters may be full. Because we can create 10 node pools with 100 nodes. That means we can have 1,000 nodes. But the real limiting factor is usually the Kube API. Maybe at some point we are sending too many requests to it and then getting rate limiting or crashing the Kube API server, which unfortunately happened in the past. So, but before we elaborate further how we can get the YAMLs inside our Kubernetes cluster, I want to talk a little bit about the environment of Kubernetes because there are different approaches. I mean, the easiest approach is writing all the manifests yourself and then do some magic interacting with the Kube API. One way of interacting with the Kube API is GitOps. I think we heard about somewhere. What it basically does is you're storing all your YAML configuration in kind of a Git repository. You can parameterize it somehow with Helm or with Customize, however tool you like it. Then there's a controller running in the Kubernetes cluster itself, pulling regularly the Git repository, building the manifest, and then applying it to the Kube API. This has some advantages like audit logging. You really know which person have changed the deployment by Git commits. And you see the inventory of your Kubernetes cluster, which is kind of great. So you don't have to scrape through the cluster with some kubectl commands. You don't need to give some guys access to it, but you can give them access to a Git repository, and then they can interact with it. The next thing is Kubernetes operators. I think in the breaks I heard a lot of things about them. Some think they are great, some think they are really not that great. So let me show you a little bit what they do. They are kind of an extension around the Kube API. I believe you already have interacted with operators because Kubernetes is built with operators. For example, in a deployment, you have a deployment operator, which is then creating a replica set. And then there's a replica set operator, which is then creating pods. And we can do the same thing with our custom resource definition. So we are building a new operator, which is then having a definition. Here we see a PostgreSQL definition. Then we can extend the Kube API, say here is some kind of YAML file, which says this is what I want to have. In the specs, we can say I want to have 3 replicas, I want to have some topology spread constraint or whatever, and hide some complexity of the entire stateful set, services, pod disruption budgets, whatever you want to have in your deployment. Then this operator is doing some long polling, which is called a watch, to the Kube API and watching his resources. And here it would watch the Postgres resource. Then it's doing some actions, it's creating stateful set services, whatever resources you want to have, maybe config map, secrets. I think this is the typical stuff. It sets an owner reference on it. That means it's getting notified when the resource is changing, because maybe some idiot is deleting the stateful set for whatever reason. And then the operator gets notified, okay, this is not what I want to have, I want to recreate it. or someone is changing the specs for whatever reason, and then the operator is also getting notified and bring it to the state that the operator wants. This is basically the entire idea. So in the top we see what an operator can do. It can create and update instances, which can also a Helm chart doing, but it can do way, way more. It can handle backups and restores, for example, and some tricky things like PVC resizers. So if you have a stateful set and a volume claim template in it, you can't mutate a field. So what you usually have to do is edit the PVC, then delete the stateful set in an orphan way, and then recreate it with the new size. And this is some operational knowledge you can build into your operator, and you don't have to manually intervene. So now we have a couple of resources. We usually build an operator in STACKIT to facilitate some of the resources, but there are also resources that should not live in the operator, like an ingress, because this is highly environment dependent. Because some use an Nginx, some use an Traffic, maybe the next guys are using Istio. So there should be resources living outside the operator itself. That's what I mean with there's some kind of ingress, maybe some kind of service which is not fitting from the operator. Now we need to parameterize it somehow, because some users want to order in Postgres with a single instance, some with a cluster. And this information from the customer needs somehow go into the YAML files. And in STACKIT, we had different approaches, and this is what I now want to talk about. So the easiest thing if you're a software engineer is building something like this, I guess. You have a client that is interacting with some network interface that you are building. Let's go back. Then it's storing some metadata in a data store. Could be a Postgres, a MongoDB, whatever you want to prefer. I usually use Postgres because SQL is one of the best languages I can imagine. You can do really, really dirty things with SQL if you go beyond like the standard CRUD stuff. And after that, we are storing the metadata. We have some async processing because it takes usually minutes to spin up a new instance of whatever you want to have. So we can't really synchronously apply. That's why there is a message queue in between. And after that, there's a message queue consumer, which is then applying the manifest against the Kubernetes cluster via some client library or via REST calls. Usually you should use a client library. This is what some guys did and easily went wrong, because what now is going wrong is the dual write problem. So they're interacting with some data store on the message queue, but what happens if the publishment to the message queue fails? Should we somehow roll back the data store, so delete the entry? What if this also fails? Then we have some dangling reference in our data store and no future processing. This is what I always highlight during this architecture discussions, that you need a consistent way. And there's a standard pattern, the outbox pattern. This means in our data store, we store the event that we want to publish plus the metadata that we want to store in a transaction. That means it's ACID compliant, especially the A in ACID, which is atomic. So it's the same idea. Then we are splitting between two clusters. Usually we have our control plane completely separated from the customer stuff, as we have seen before. So the REST API is somehow different than the customer instances. So we can scale them individually, and we can have multiple clusters running with the customer instances, which is what we wanted. Then we encounter some problems sometimes that maybe we can't access the Kube API from the public because maybe the Kubernetes cluster is running in a customer project and here's some ACL. That means we still need to interact somehow with it. And instead of going the push approach, like before where we have our message consumer pushing to the cluster via the public endpoint of the Kube API, we can use an in-cluster config. That means the agent, I will call it a message queue consumer, can consume the message via a pull mechanism. I think there are different approaches when you use a message queue. I think RabbitMQ is still using a push, and Kafka is using a rather pull approach. But here we should have a pull, otherwise we run into the same problems. And then again, we are generating the YAMLs, apply it somehow, and the instance will start. because then Kubernetes is running through. So why have I brought up Argo and InfluxDB as a GitOps tool? Because at some point, let's go, we played around with different ideas and figured out maybe we can put all the YAMLs into Git. So each instance also needs to be pushed to a Git repository, which is then pulled from the GitOps tool and then applied to the cluster. This sounded really great because then we have a unified way of getting the YAMLs into a Git cluster because we are running our initialization via these GitOps tools. But then you have to consider that you may run into scaling issues because you can't have two pushes at the same time, so you can't multi-thread it because only one thread can push and then the other thread has to pull again the state and then push again. So you have to find a synchronization mechanism via some topic modeling, for example, via some distributed logs or whatever. And this was really not that great. The other problem that we encountered was rate limiting from the Git provider. We were using Azure DevOps, and at some point it was done really, really slow and terrible. So I can really recommend not put everything into Git. And the next stuff is an idea we stole from Gardener, which then stole the idea from Kubernetes itself. Because if you're looking how Kubernetes is scheduling a pod to a node, there's usually a kubelet running on the node. Then it's doing some matching with scheduling and watching on the kube API server, can I schedule the pod on my node? And if yes, then it's applying that. That means instead of a kubelet, we have an agentlet, so to say, on each cluster. And now our REST API is creating a database entry, so to say, in the kube API, because behind the kube API there's a SCD, so it's a distributed QL store. There we can store our metadata, like the replicas, a name, a description, whatever we want to have. And then this agentlet is an operator which is watching this data entry and then can operate, which is kind of a great idea, I would say, until you have to include external dependencies like an audit logging system, a billing system, because then it starts to fall apart, I would say. Because then you have to use the outbox pattern in the NoSQL context, and you start to create anti-patterns, which is really, really ugly, because you have to set finalizers for audit logging, because you have to transmit the audit log event, and it should not be deleted. I will skip the discussion and maybe spare it for later. So now we are getting the YAMLs somehow in the cluster, but we also need to get the information back from the cluster because the customer wants to know what's the state. Maybe not even the customer, but also tools like Terraform, Pulumi. We have seen it's applying something and then it's waiting, right? It's waiting for until it's ready. So we need to propagate back the state of my Kubernetes cluster to the customer. That's what I wanted to show here. Somehow in the data store, I need to mutate the state from the Kubernetes cluster. The easiest way is doing some kind of pull mechanism again. We have our cluster in this management lane. And then we have kind of a status worker, which is pulling the database for an instance that it want to check. Here we can avoid pulling multiple instances at once, maybe pulling it too often by having some kind of timestamp and then checking based on the timestamp if we are needing to check again or not. And in the Kubernetes cluster, we can build our product operator logic into it and get a state in the status field. The easiest way is we have kind of a stateful set and there are ready replicas in it. And if it's bigger than one, maybe the instance is already ready. So this is what the status worker is basically doing, interacting with the kube API, getting some status information field, and then writing it back into the data store. And the REST API is then reading from the data store again. But this has one downside, that we are checking regularly, because we're also checking if there is no state change. And to avoid that, we can use the power of Kubernetes. As I said in the very beginning, there's this operator which can watch his own resources. So here we have an agentlet, which is then watching his product resources, like a Postgres, for example. And whenever this status field is updated, we can publish a message to this message queue, and then there is this the status worker, which is then updating the status in the database. So we are avoiding this multiple pulls all the time when there is no change at all, because the Kube API will notify us if there is a change, because it's the entire idea of having watches. So instead of having this message queue in database as before, we can build around the Kubernetes idea. So as you have seen before, there's some kind of operator which is watching the instance and then creating the YAMLs, and we can use the same flow to get the information back. So we have the operator which is watching his resources, which then is changed at some point, then he's getting notified, adding it to his database entry in the Kubernetes API itself in a status field, and then the REST API can query the status field. And once we have established this kind of way of getting resources inside the Kubernetes cluster and getting information back, we can also use it for all kinds of other resources, configuration that we want to have. And I think that's the greatest way. Once you have the standard pattern, you can just apply it and are done. For example, here we have a backup CRD, and I showed the approach with the Kubernetes approach with this agent-led again. Really the same thing. I think this is what the Postgres operator is doing. So this brings us to the end of the talk, I guess. I think all proposed approaches are really valid, and it really depends on the use case, what you want to do. But you should really consider measuring some performance impact, because we recognize that we crashed the Kube API at some point. Then you need to really be careful to avoid this problem, because once you have this architecture running, you can't easily change it. That's why you should build some kind of MVP and do some measuring. And then there's Ivan. It uses, for example, this database plus queue approach. So not everyone is building around this Kubernetes approach, I would say. And that's it, I guess.
Thank you very much. Yes, there are questions. One moment. Ach, mit links kann ich doch nicht werfen.
So you said you crashed the Kubernetes API. What was the limiting factor? So it scales on its own normally, right? It has also multiple instances and can be scaled up. So where were the limit and what exactly was limiting, like etcd, or what was the problem?
I was not really sure what the problem actually was. I think we had a namespace with a lot of pods, with hundreds or even thousands. And then the operator listed the pods over and over again, and then was not one operator, but like 10 operators. And this caused a lot of pressure on the etcd and the Kube API server. And at some point, the Kube API server had around 40 GB of RAM consumption. And we believe the problem was listing of too many resources in this namespace.
Okay, the next question is in the back.
Thank you very much for the talk. Very good thoughts, in my opinion. But the one question which was left open for me is, if you use all those databases and RESTful APIs and queues to get your stuff into your clusters, where do those services run, and how do you prevent drift in those systems?
Drift in what way?
Well, how do you provision those systems that provision your clusters, and how do you manage them and keep them in the state they are supposed to be?
Yeah, this is a one-time effort, I would say. So we are using Terraform, even though it's not that great, but this is one of the options we have. I think that's the only one option we have in our cloud. So initially, we are provisioning kind of an Azure DevOps repo, an initial Kubernetes cluster where this management lane runs. Even this customer clusters, I would say, are also permissioned via this Terraform, and then initialized via the GitOps stuff we have running. The same applies also for our management lane cluster. Also, the GitOps thing will run the components that are living in there. like Cert Manager, external DNS, Prometheus. I think there's some standard components we have in every single cluster.
Okay, thanks. So there are dedicated management clusters in which those services run?
I think Terraform is run by a pipeline.
Okay, thanks.
Okay, no questions anymore. Thank you very much, Patrick.